Hey, Thomas.
Hey, Luca. So,
How's it
how are
going?
things?
Oh, wow. Yeah, not much happening in AI, right?
I don't know.
You know, I
Have you heard
this
anything new?
yeah, yeah. So, yeah, and I'll tell you how I heard it. Well, I heard it before, but the story is nice. So, on what was it? Tuesday, I go to the hospital for a checkup, periodic checkup. At certain age, you need to be checked periodically, or at least that's what they tell you. And everything is fine. I have an exceptional state of health, which is great. But I was waiting in the waiting room, and there were three newspapers from Italian newspapers: Il Sole 24 Ore, the economical one; Corriere della Sera, one of the national ones; and Eco di Bergamo, the Bergamo one. And all of them had this story on the first page about this AI model that came out. So
Right. It
yeah,
has been very similar in the German newspapers too.
yeah. So I said, and I had this realization where I said, "Oh wow, like, this is really coming." Yeah, it started out as a niche a few years ago, right? When we were just dabbling with it, but now it's on the first page and people were talking about it. Okay, great. And so yeah, this R1 happened, and I mean, I've been playing with it. Of course, we've always been playing with it, and it's not hard to understand why it is a kind of a seismic moment. Because no, maybe not because of the model itself. The model is great, but it's a recipe that came out that is the what kind of shuffles all the cards. And
Yeah.
it. And I also found interesting that a number of people had tried the same recipe a few years ago, but the base models were probably not capable enough. And now, because you need a policy for reinforcement learning, that it's already kind of almost there, kind of quite there, or at least partially superimposed with the final one.
Yeah, but so there is actually, I think there is someone who like did a little demonstration of an R1 like policy with a small model.
Yeah, yeah, on a
I think I
math
saw
data
that the
set.
other day. Hmm?
Yeah, on a math task. Yeah, yeah, yeah.
Right.
But but in general, I think the gist of it is that base models nowadays are much better than what they were 2 years ago. And so, well, and so now they can become a kind of a base for a pure RL strategy, which is great. Which kind of changes everything, because one of the limitations of adoption of AI in the industry is the need of curating a lot of data. And it's not that the reasoning model saves you from that. You still need to do it, but you can use a very capable model to do it. And so it's kind of a flywheel that has its starting point there. And right now you can deploy it on your own premises, or if you have the right tools. And of course, we're at Lightning, we're very busy making that happen. Uh, uh, then you can have your flywheel privately and internally, and that is a big unlock. And
Right.
yeah, it's great. Overall, it's great. And then we will, as our Thunder session goes, we want to take a peek at how the sausage was made, right? In our
Right.
style.
And of course, basically, we've been making sausage ever since Tuesday, right?
Absolutely. Of course, of course. So the interesting thing starts from this report, and then actually a couple of weeks ago we had an episode, and we called out the DeepSeek V3 report, and we said, "This is great. This is like, you know, we
Yeah,
mentioned it with Thunder being, you know, all the things that uh, and all the optimizations that ended up in the DeepSeek V3 paper are optimizations that pertain to program transformation. So that's why we found it really interesting. And but yeah, this has spiraled out of control since then. All right, so today we'll kind of try to understand a bit more of what R1 is. There are multiple R1s. There's a 70 billion R1. What is that? Or 34 billion R1. What is R10? What is DeepSeek V3? So we'll try to make a map of the world. And then we'll dive into, architecturally speaking, what is DeepSeek? And then we have a surprise at the end, which is a mini DeepSeek that we're kind of using to reason about what are the challenges when you have a model like that. And also we can use to make a parallel between the paper and the implementation. So very exciting episode.
Right.
All right. So let me first draw a map of the world, and then we can start diving in very quickly. So we mentioned DeepSeek V3, which was this big model. It was already MOE, 670 billion parameters, with, how many are they? Like 34 billion active parameters.
I think technically it's 671 billion, but
sorry. Yeah, one.
If you Google it, it would pick up 671. Not that
one.
1 billion, give or take, right?
Really, okay.
You remember when like a few hundred million was a lot of parameters? Now you just
Well, you feel it though, right? Because even downloading this thing, or where do I store it? Yeah. Okay, great. So DeepSeek is trained using next token prediction. Oops, sorry. And actually, there's a trick here where you predict multi-token. So if you read the report, you see that there's something there that will can have an implication on inference too. But essentially, it's a traditional MOE with many different things inside that make it a bit less traditional. But you can think about it as a next-gen mixed trial model, more or less, conceptually speaking. And then what they did, and this is a base model. So not supervised fine-tune, not RLHF. They took the base model, trained on a very, very many tokens, I think 15 million or something, trillion or something. And then they applied, so DeepSeek applied a RL process to get to DeepSeek R1 0. What does 0 mean is that here they created an environment where the model was given tasks that are verifiable, meaning, give me the result of this operation, and the model had to figure out how to compute that operation, and then output the final number, the final answer, that would be verified by code, just by typing in some math interpreter, formula in some math interpreter, and say yes or no. Is it correct or not? It's a reward signal. And so what they saw is that the model was encouraged to think, meaning emit tokens at the beginning that were included between two tags, think, and then closed think, right? And here, the model could emit tokens that were not the answer, but they were useful in producing an answer. So it was given the space to do anything there, but then to produce an answer outside of the think block that would be the right answer. And so there was some freedom here left to the model to manage the length of this thinking section. And what they saw is that the length of this section, if this is the length of this section, and this is the training iterations, would start growing in
Yeah.
time as the model was learning how to think, how to process, and get to resolutions of problems. So this phase produced something that was already capable of solving a lot of problems, hard problems, although the output that it generated was not optimized for readability. So it would generate something that was half Chinese, half English, half whatever, ramblings, repetitions. But the thing is
Italian.
that, yeah, oh, Italian, surprisingly, yeah, gesticulate and so on. And yeah, and so the zero model is an incredibly capable model, but it's not very nice for consumption of the thinking process, for example, the chain of thought. This is called chain of thought. And then, so the DeepSeek team created R1 through a process that had 3 stages where you did some RL, some supervised fine-tuning, some RL, some supervised fine-tuning. But interestingly, the supervised fine-tuning data was coming from a previous model. So it was generated and ranked for quality, probably partially manually, but not really labor intensively. It was all based on the previous iterations of the model. And so this is what we when we talk about the flywheel.
Like OpenAI says that they took some of the other models to help along, but yeah.
Well, it's
I mean,
it's a tricky position to be it.
Look at my stuff. Never hurts to claim that.
Yeah. So yeah, and this whole thing generates a bit of a flywheel where at the end of the process, this model is a model that can generate this chain of thoughts very high quality. And so these can be then used to generate data sets that you can use to supervise, fine-tune other models. And so what happened is that they took Llama, 70 billion, and 8 billion,
favorite.
and Quen, 34 billion, and I don't remember others, but and they did what it's called distillation. It's basically taking the outputs from other models and supervised fine tuning with the input output pair from other model from the R1 model, these other models. So now there is a DeepSeek 70. When you find 70 billion, 8 billion, and 35 billion, these are basically the Llama 70 billion, 8 billion, and 34 billion with the distillation from the R1 model that, the distillation is just a collection it's a collection of chain of thoughts and outputs and inputs, of course, that were used to supervise fine-tune the model. Okay, this is the map of the world. This is what happens. So you can use either of them. Of course, if you use the fancy 671 billion, you will have a certain quality, but you need to spend a lot of time and money getting it to work. And this is why Lightning will make it like super easy instead to do that, and enable organizations to do this internally without a lot of infra challenges. And you can also take these models. They're a bit less capable, but they are still reasoning models. So they're prompted to reason. One of the interesting things for reasoning models is that you can follow the reasoning. So you will know if the model is following a certain process to get to the right solution. And I've seen people taking only the chain of thought and sticking it into another model to code, for example. That other models may be better at coding, but with the chain of thought, they will produce better code. So if you think about the enterprise and what this can mean for organizations, that the implications are pretty profound. All right, I'll stop here. So, all right, so this is the first thing. The second thing is, as we saw, DeepSeek R1 is a derivation of DeepSeek V3. And here we find the technical report again that we showed the last episode. And so today, what we want to do is to take a look at how this model is built architecturally. And Thomas has prepared a very nice surprise, which is a mini R1 that we can take a look at. So we'll spend another couple of minutes looking at this figure, and then we can jump straight into the code.
Yeah.
All right, so what is this figure showing us? Okay, we know transformers are blocky models. There's an embedding at the beginning, and there will be a head at the end. But essentially, what is happening is, we have a bunch of transformer blocks. And if you only look at, let's see if I can do something fancy. Great. If you only look at this part of this figure, it's no different from any transformer blocks, right?
Right. Standard Llama.
Yeah, exactly. All of them are the same. RMS norm, attention, RMS norm, feed forward. But what happened in DeepSeek is that, well, let's start from how is this an MOE, a mixture of experts? Mixture of experts means that you can scale up the amount of parameters in the model without scaling up the flops needed to deal with them by breaking up your feed-forward network into smaller ones here and having a router that decides which ones will be active at a given time for a given pass. And so maybe in this case, this in red will be active. For another pass, others will be active, and so on. And this router is basically a matrix multiplication that decides where you should route your thing with some nonlinearity on top of it, because it's a gate. And every gate needs some nonlinearity, otherwise it's not a gate. And we'll look into that in a second. And then the other part is the multi-head attention that has a particularity in which we know multi-head attention as KV and Q. And key querying values. DeepSeek adopted something a bit different where you have latent variables, which is just a vector, from which they extract, through projections, they extract the query key and value, right? And so there's a saving there, because instead of storing the infamous KV cache as a whole, you can store the C's here, from which you can generate the key and values through projections. So you're gonna save a bit. This massive model, if you had to store K and V for everything, it would be a lot. Like, how many layers does it have? 60, right?
61.
Yeah.
Layers, actually.
So, yeah. So a lot.
And there's a bonus layer number, like the 61s are 0 to 60, and the bonus layer 61 is the one you mentioned in the beginning for the multi-token prediction, right? But
we'll cover multi-token probably some other time. Yeah, exactly.
Right.
Anyway, this is clear. So we have a different formulation of attention with the latent instead of the KV and Q explicitly.
More precisely, we have the latent in addition to a bit that is like the traditional one with the rotary embeddings and stuff, right?
Oh yeah. Here, this one and this one.
Yeah.
So yeah, it's a bit more involved, and then we have the MOE part. So if you had to write it, start from Llama or Nano GPT and write this model, you would start from the standard formulation, and you would have to replace the attention block and the linear and the feed forward to reflect these things. So I think now we can go in and see the structure, because this will be instrumental in understanding why and if this is hard to compile, because ultimately we're interested in that. Great. I'll pass you the ball.
So let me also share my screen, and let me find the right studio. So here you should see the DeepSeek mini model. And so what's going on here is that I took from the repo, the DeepSeek v3 repo, I took the model, and they have a inference only model that they give you the source code from, and we've simplified it a bit, but not that much. And then I made up, to be able to experiment with it, I made up a few parameters that make it smaller. So instead of 60 layers, we have 4, and we could probably like go down even further. And so yeah, so if you look at the model in the how it is implemented, you see that you have the transformer, which is just the standard transformer. You have the embedding, you have the layers, and then you have a final RMS norm and a head, which is this LM head in the GPT. And then the blocks, they have 2 kinds of blocks actually. So the first few blocks, I think in the real model, it's 4 or 8. That are dense blocks, they call it. Well, actually, it's 3. I just looked at my cheat sheet. So here we have one block that has a standard MLP that is, I think, pretty much identical to the Llama MLP. And then for the later blocks, they have this mixture of experts. You can see there's a gate module, and then you have experts here. I made 64 experts, but the full thing has 256 experts per layer. So that's quite a
That's
bit,
a large
right?
number. Yeah.
Yeah, and then there's the shared experts. So funnily enough, relative to the figure in the paper, the number of shared experts in the full model is set to 1. It's a fairly large expert, but nonetheless, so this is about as large as one of the
Yeah. To
experts here.
clarify, the shared expert is an expert. Conceptually, MOE, when it's time to compute the forward pass at the MOE, there's this gate that is computed, and that tells
Right.
you which ones will be 0 and which ones will be zeroed out and which ones will be picked. And so a different number of experts, fixed number of experts, but different experts will be picked. And then there are a few experts, which are the shared ones, which will always be there.
Right.
And so, yeah,
And
for all tokens, that one will always be active.
maybe we just and basically I mean, it's the vanilla code. I took out any external dependencies to make it really self-contained. But so the transformer module, that really looks like just about any transformer model. And
Yeah,
then
the fracs are the
yeah, they
rotary
have
embedding.
that. Those are for the rotary embeddings. They do complex ones instead of doing it like LitGPT. There's also this thing with the mask, which is kind of using the start position here and the length, which is like a bit tricky when you want to do compilation. So LitGPT, for example, that passed in the input positions, right? And
Yeah,
also Hugging Face, I think the Transformers library
yeah.
uses
Yeah,
it.
just to clarify, this code has been released by DeepSeek as a reference
Yeah,
implementation. And
and
there's a lot of
and it
optimizations that we are doing on top of that, of course.
right, and it's amazing that they did it right. And so
Yep.
here's another thing, like there is an option to use FP8 for the linear layers, and we will see how that works in a bit more detail. The transformer block, again, doesn't have really many surprises. There's this, for the dense layers, you have the standard MLP. Otherwise, you get the mixture of experts. And then it's attention and feed-forward network with a couple of RMS norms and residual path. So nothing new here. And now we get to the mixture of experts. And so this is like we saw in the paper. There's this gating network, And the gating network basically gives us weights and indices, because it would be like wasteful if we had all the weights and many of them were 0. So it just takes the top few weights, and they observed that keeping just a few. So I think it's 8 of 256. Keeping just the top ones will do nicely. And so,
Yeah, let's take a look at the gate. If you scroll up, there's the gate class.
yeah,
I think.
so the
Yeah,
gate look a bit involved, but really you have a linear layer here, which is just a matrix multiplication, right?
which is what learns how to get
Right. So
route, essentially.
based on the input, we determine like routing weights. Traditionally, you would just take the softmax as the to move it to a probability distribution. But so in the DeepSeek V3, they tried something different. They took a sigmoid here, and then at the bottom they normalize it to 1.
Yeah.
I'm not sure like what the exact reasons are.
I think it's
But
just simple. Like, I
yeah,
think it's just simple because they don't need a probability, because all it's needed here is the ranks, because you do a top K. And so you
well,
don't need it to be calibrated, right?
yeah.
Or not?
In the end, you would if you have the top K, you lose a bit of probability unless you sorry, unless you do this renormalization anyway. So
Right, right. But it's not
probably
calibrated. It's uncalibrated, like uncalibrated 0 to 1 numbers that rank
right.
consistently. Maybe. Yeah, that's my
Yeah,
interpretation. I don't know.
and then they have a bias that they use when the dimension is like a particular number. It's interesting that it's
Oh,
equal and not greater or equal, but you don't want to have everything 0, right?
yeah.
Um, and then you basically take the top K here. Oh, the group scores. If you have groups, you can have uh, uh, multiple things, or you do this. How do you do this? The evaluation is in groups, or
Yeah, they have actual groups. I think this has to do with a consistency thing that they have. It
all
might
right,
be
yeah. So
for routing consistency to kind of encourage tokens to go from the same sentence to go to the same experts and stuff like that, I think.
yeah. So
During training, not during forward, during training. Yeah.
yeah, I think you basically pool the experts and then make sure that
Yeah.
it's kind of similar things, and then you basically take here the top scores and the weights. You make weights that sum to 1, and you scale it with the routing weight, which is kind of I think it's an argument. It's not a learned
Yeah.
parameter, where you have the weight between the terms of the sum, right?
Yeah. And here, I don't see anything particularly gnarly with respect to compilation, right? We don't have
Well,
data dependent stuff, or
I
yes.
mean, there's details that will like make the compiler work, but it's not
Yeah.
that bad.
Mhm.
And of course, like Thunder would make these in-place operations out of place, but it's not bad. So
Yeah.
the trouble that many compilers have is with dynamic shapes. And
Yep.
it's not only the compilers, right? It's also like the remaining infrastructure. Things like CUDA graphs don't really work well with dynamic shapes.
Yeah.
And so you have here that because you have the mixture of experts, you of course only want to compute it for the experts that actually contribute to the final output, like the 8
Mm-hmm.
ones, not the 256 ones. And so what it
Yep.
does here, it has a loop over all the 256 experts, and then it checks like uh, how many
Yep.
tokens go to this expert. If it's no tokens to this expert, we do nothing, and otherwise we grab the tokens that we want to use this expert on, and run it through the expert, and then add that to to the uh, uh, the activation, right?
Yep.
And then we have the shared expert, and the sum of those is ready to go, and the residual path is in the block, right?
Yep. Perfect.
So
So yeah,
that's,
this is the MOE, and we are
yeah,
staring at it. Only that it's gigantic in R1, but yes, that's the thing.
right. And of course, the expert is pretty much the MLP layer too, right? So we
Yep.
have, similar to what we had in Llama, we have the silo times this W1. I don't know what the numbering is, but yeah, so this I think is called the gate sometimes. And
Yeah. It's always like that. I've
you
always
have,
seen this number. Yeah.
yeah, you have the top part, which is the W3, ironically, and then you have the bottom part, which is W2. This is that, and we have the gate. We looked at the gate. The MLP looks identical here. Um,
Yep.
and then we have the
Ooh.
multi-layer attention, and that is scary again. And
Yeah.
so if you look at the usual attention, you have that you do this uh, that you compute the Q, K, and V. And so you take the input and apply a linear layer to all three of them. Um, and this would be like for the Q, this would be the equivalent here. But so they actually have this low rank uh, thing going on. And so if we have the low rank decomposition, it actually does like the first half of the low rank, and then it does the RMS norm inside the
Mm.
low rank representation. And then it applies the second factor of the low rank decomposition. Um, yeah, and so the other part that is interesting, if you follow this in great detail, and I know that it's hard here, so then they split the queue into the part that doesn't use rope and one that
Nope.
use rope.
Is that
Um,
nope?
yeah,
Nice.
it's nope. And it's
Nope,
called
because it doesn't
no
use rope.
positional embeddings, right? Because it's
Yeah, yeah.
independent of the position. And
Yeah, it's
so
pretty
the
funny.
QPE could also be called Q rope, because that's like here
Yep.
they call it rope in the arguments in the
Yeah.
configuration. But yeah, so the interesting part, this just goes the usual way, the QPE. But so the interesting part perhaps is that later on we multiply the QNOPE, like the no P, the low rank bit, with a thing that is the second factor of WKV,
Mm.
of the KV weight, and it's the second factor that is this B. And so the interesting thing here is that when you have two low rank decompositions and you multiply the matrices as you do for the weight matrix in the attention, for the attention weight matrix, what they do here is pretty nifty. They multiply the second factor of the k to the q, and so they put in only a low rank vector into the attention itself, um, which I thought was a neat trick. I don't
Yeah,
know
it's
why
super
they
neat.
have a shared they have a shared parameter here, because they are using the two bits separately and in totally different positions. So you have the first part here, and then the second part, I think, is somewhere here, right? So that is the second half
Yeah.
of the decomposition. But so the interesting thing maybe is that the first part is truly shared. So The
Yeah.
KV here is the first factor, and that is shared between the keys and the values. And you see that also if you were to rewrite this attention here, which is like spelled out using einsums. If you make it use the torch function scale dot matrix product attention, um, then you see that it enters the k part twice, because it's the first factor of the k and the first factor of the v is the same, except for the PE stuff, the rope stuff. Yeah, so this is the attention.
Very neat.
And it's pretty neat. I'd probably, if I would write it, I would write it a bit differently. But maybe they started out with a dense attention, and then it made sense to organize it that way.
Yeah, I feel like, as I said the first time we went through the report, that there are a few papers in that report that normally wouldn't be published separately at conferences.
Yeah.
It's very interesting.
Latent attention is all you need, or something like that.
Yeah, exactly. Yeah.
Okay, and then they have an RMS norm, which is not terribly interesting. But so we talked about FP8 during the last episode from Bergamo.
Yeah.
And so you can see it here in the linear that they have, when you have here the FP8, then the weight itself will be FP8, but also they have this scale factors, which are for block size, and the block size here is 128. So for every 128 weights, they also, or if it's a 2D thing, 128 times 128 weights, they have a scaling factor in float 32. And this has been something that, like for using FP8, this has become, and also for quantization, of course, this has been kind of the standard thing, right?
Yeah.
To do this blockwise thing, and it's gone so far that they actually like standardized a type where you have a vector of FP8s or even lower, FP6, FP4, and then have a factor for every, I think that is one dimensional, right? The MX FP8.
The new one. Yeah. So hardware now will start understanding that thing.
Yeah. So this is like I made a manual dequant, so they ship a Triton kernel with it, and you need like a Triton 3.0 based torch to run it. If not, it will crash. If you're using like torch 2.2 or so, it will just crash without comment. But so I made a little thing that does the dequantization manually. Basically, you just multiply with a scale here on one of these tiles, right?
Yeah.
And that's it. Like that's the entire thing, and that's very neat. And kudos to the DeepSeek team that they have 350 lines. It's the full model, right?
It's amazing.
And then you can
300 lines, 600 billion stock market loss.
Yeah, that's quite effective. And so, but one thing you certainly see here too is that programming, like it's really that you don't write the code what to compute anymore, but it's all in the weight, right?
Yeah, for sure. And then in a lot of these 300 lines are also tricks that you need to do to compute it more efficiently, or to break things up. That could be transforms again, because it's kind of a mechanical code transformation that has been kind of baked in the code, but the semantic expression of the model itself, it's even shorter than this. So yeah, for sure, it's in the weights, and the weights apparently can kind of grow by themselves a lot. You give
Right.
them a crap ton of text and then some hard tasks, and then it figures it out. It's like the bitter lesson. Um, yeah, it's pretty amazing. Unconstrained chain of thought. So anyway, I think the testament here is that now we know it's possible. It's like ChatGPT. Now, the recipe was clear at some point, and now the recipe has simplified, and it's
Right.
everybody can try it out, and maybe it can be miniaturized even further. So I don't know. We're living interesting times. So this
Yeah.
is how the sausage was at the very core. And then, yeah, we have some surprises coming up in the next few weeks. We'll start using models more and show you the
Yeah.
effect of some optimizations. And yeah, we're looking forward. It's
Yeah.
very exciting.
Super good.
Awesome. Thank you, Thomas, for taking us through the code and seeing there are
Yeah.
no secrets, no esoteric stuff, but a lot of thought went into those 300 lines. Um, bye, everyone, and see you next week.
Yeah. See you.